Good morning, everybody. Welcome to a new IFIMAC colloquium. Today we have Florian Marquardt from the Max Planck Institute in Erlangen, so the Max Planck Institute for the Science of Flight, and he's also appointed as a full professor in the University of Erlangen and Nuremberg. And now let me tell you a little bit about the background, essentially, of Florian. Okay, so Florian studied physics actually in Bayreuth in Germany. Okay, and got his diploma in '98. And then he moved to Basel in Switzerland to do the PhD with Christoph Bruder. Okay, so also well known here in Madrid. And after working essentially in different topics, especially on dephasing essentially in different solid state systems, he moved to Yale as a postdoc, and he was working mainly with Steve Gervin, okay? In particular, essentially in optomechanics, where he's one of the world leading scientists in this field. And after 1.5 years, he returned to Germany, essentially as a junior professor and leader of what is called Emineta Group in Munich, in the Ludwig Maximilian University in Munich, one of the two best universities in Munich. And short after that, he got an offer essentially from the university in Erlangen, Nuremberg. And ever since, basically, he's a full professor. But in 2016, he was also appointed essentially as a director of the Max Planck Institute, a great honor. Okay, and he's actually sharing the two positions. And Florian, you told me essentially you're a 20% professor in Erlangen, so he has actually two jobs. And among the different essentially research fields, he has been doing way too many things. Okay, so like from topological transport in phonons and photonic systems, but circuit quantum electrodynamics, optomagnonics, nonlinear classical field theories, and many other things. But in recent years, he's really well known because he has been one of the first condensed matter physicists to realize of the potential of machine learning and artificial intelligence, basically in disciplines like physics. And actually, he has been teaching essentially a very famous course that you can find online and in different essentially podcast platforms that I follow myself essentially during the pandemic. Okay, and actually we asked Florian today to try to bridge the gap between essentially, in particular, quantum technologies and machine learning techniques, essentially, and we're definitely looking forward to your talk. Thanks for being here.
Thank you very much, Carlos. Yeah, I'm glad to be here. Thank you all for showing up. So today's talk will be about how to use machine learning for improving quantum computers and other quantum technologies. And just a big disclaimer in the beginning, I will be talking about classical machine learning, so the kind of machine learning that computer scientists have developed over the past decades. There's also another topic that is equally interesting, but is separate, which would be to even use quantum computers to do machine learning, but that's something separate. Now, let me start with a very general introduction. So if you think of your brain, you can view it in many different ways, but one possible way to view your brain is as an information processing machine. So you see something or you hear something, that's the input, then you process it, and then there will be an output. Maybe you speak a word or you perform some action. Now, one of the amazing things about this information processing machine is that in contrast to an algorithm running on a computer, it is extremely flexible and robust. So if you see a picture of a light bulb that you have never ever seen before in this particular shape and perspective, you are still in a fraction of a second able to recognize it as a light bulb. And so the question is, how does this come about? Now one can go and look inside the brain and look at the hardware and realize that it's just lots of neurons that are interconnected and between which electrical pulses are running around. So this is a famous hand drawing of Ramon y Cajal from 100 years ago, who was the first to look really at these neurons. But it's essentially a very complicated electrical network. And in some way, this electrical network is able to shape itself by training, by looking at many different examples, and then eventually generalize and see, oh yes, this is a light bulb, even though I've never seen it before. So more than half a century ago, people came up with the idea, why don't we try to reproduce this on our digital computers by building artificial neural networks that are at least inspired by the brain. Especially, these would be complicated connecting structures that are made up of many similar looking units, and where the idea is also to train them. So you look at many training examples, you know the correct label for the particular given image in this case, and you would adapt the internal parameters of such an artificial neural network, in this case the connection strength between the neurons, in order to make it produce the labels that you have shown it. So this is the kind of training that's going on in this field. And even despite the fact that the basic ideas had been around even by the 1950s, it took many decades to turn this vision into a reality for several reasons. First, people were lacking compute power, and they were also lacking the big data that is really required to train successfully. But eventually there was a breakthrough, and maybe the main milestone was in 2012, when for the first time ever a neural network was able to beat all the other approaches in the field of image recognition. And since then, they have not only excelled in this field, you all know that there have been so many breakthroughs. For example, nowadays, neural networks can produce for you text that at least superficially looks like it could be produced by a human. It can produce photorealistic images based on a description of the image, and many more things, especially also in science. For example, many of you may have heard of AlphaFold, so solving the protein folding problem. Okay, so that raises the obvious question, and has raised the obvious question already several years ago. Can we also start applying these tools for the purpose of improving quantum technologies? So the picture you have in mind is, here's your little quantum computer chip, if you like, or other quantum device, and you want to connect it to a neural network or some machine learning technology, and hope that the combination of the two will improve things. And there are actually many different directions you can take this. So if you are interested even in describing a quantum device, you may have to look at the wave function, and if this quantum device is consisting of many particles, then the wave function, as you all know, it lives in a very high-dimensional, exponentially large Hilbert space. And so there have been people using neural networks in order to represent quantum states efficiently. Also, you may have fabricated a quantum system, so you kind of know the Hamiltonian, but the parameters inside the Hamiltonian, maybe you haven't yet calibrated them precisely. And machine learning techniques can help you in better calibration of such a device. Then in order to do the calibration or to do anything useful, you will have to carry out measurements. Measurements in reality, in real life, look like very noisy traces. Voltage versus time looks noisy. And you can use neural networks with their pattern matching power in order to interpret the measurement data and say, oh, this noisy trace belongs to a qubit that is in the state 1. On the other side, I show some of the maybe higher level conceptual things that you could do. So you could set yourself the task even to discover an experimental setup, put together different components in order to optimize some aspect of what you want to do. Or you could zoom in and look at the hardware level control. Which shape of the microwave pulses should I send down to my quantum device in order to achieve what I want? Or you can take a middle ground where you say, I already know how to do individual quantum operations. I have optimized the pulses for those, but which sequence should I take, maybe including some measurements and feedback in order to implement interesting quantum protocols, including quantum algorithms running on a quantum computer. So you see there are many different things where you can take this. And for all of these, there are at least first works establishing as a proof of principle that something can be done, but there's still a long way to go to make it really useful. So before I go on for the rest of this talk, I just want to briefly mention, as was said before, our group really focuses nowadays on this interface between machine learning and physics. We're looking in different possible directions. For example, since we're at the science of light, we're interested in photonic systems and how can we optimize, improve photonic systems if we're exploiting neural networks for that. we have been looking into physics for machine learning in the sense, can I implement interesting hardware, so-called neuromorphic hardware, to build devices that are very energy efficient and can do the things that neural networks usually can do. But then this talk today will be a little bit more about these two topics here on the right. So one is machine learning for quantum technology in general, and I will talk a little bit about quantum error correction. And the other more general topic would be artificial scientific discovery. How can we make a computer mimic a scientist in order to give us maybe even interpretable results, interpretable discoveries. So in this talk, I will split it into two pieces. In the first piece, I will tell you something about discovering strategies, feedback strategies for quantum computing devices, for example, for the purpose of quantum error correction. And in the second part, I will tell you something about how can we make the computer discover for us good scattering setups, which implement interesting functionalities for waves propagating through such setups. Okay, so that's the plan for today. So let's start with this first topic. How can we discover better strategies for quantum computers? And in order to set the stage, say 90% of what is done for neural networks falls under this heading of supervised learning, which really can be viewed as a situation where you have a really smart teacher who knows all the answers to a large range of questions and is telling the student, and eventually the student will not only have memorized them, but is also able to slightly maybe generalize or interpolate between the different answers. The problem with that approach is the final level is obviously limited by the teacher. You will never become better than the teacher. If the training data is bad, then also the student will be bad. However, if you are a very ambitious student, you want to become better than your teacher, right? Or if you're a scientist, you have to discover new things that no one has told you before. And so that's the domain of reinforcement learning. So if you're faced with something completely unknown and you want to solve something, but no one tells you the solution, what can you do? Well, the first thing to do is just to try out things, and then it doesn't work. To try out a second thing, it doesn't work. To try out a third thing, and maybe it works, not very well, but a little bit. And so you keep doing this third thing, but with small variations. And then you keep the variations that work, and eventually you become better and better and better. And this is the domain of reinforcement learning, because you're reinforcing the good actions that were successful. And so it's really here about discovering strategies to solve problems, strategies to control something, feedback strategies, that kind of thing. And so very famously, maybe the most well-known example in this domain is when back in 2016, 2017, the company DeepMind used a neural network and reinforcement learning in order to teach it to play the game of Go and become even better than the best human players in the world. Even though this game is considered very complex, much more complex than chess, because there are so many moves that you can take. So how would a computer scientist look at reinforcement learning? They would split the whole world into two pieces. One is the reinforcement learning environment, which is really all the world around us, maybe this stack of blocks. And then there would be the agent. Think of a robot or something else that wants to manipulate this environment and become successful at some task. So this agent would take in observations and then would try to map the observation onto an action, onto a suggested action of what to do next. And then it will apply this action. This action will then, say, move around one of those blocks. And because of that, the state of the environment has changed. And so you take in the next observation of this changed state of the environment. And so you go into this kind of loop, into this kind of feedback cycle. So what happens in reinforcement learning is you will try out actions. In the end, you will get a reward, because someone has to tell you, if not how to solve the problem, that's your task, but someone has to tell you what is the task. So for example, in this case, maybe if you stack these blocks to a very big height, then you get a large reward, and so that's good. And so what you will do is you run through this game many, many times, sometimes get a large reward, sometimes get a low reward, and eventually the goal is to improve this policy or strategy in order to become better and better at the given task. So that's reinforcement learning. And so if we want to apply this to the specific domain of quantum technologies, our environment could be maybe a small set of qubits. The observations could be measurements carried out on these qubits. And the actions could be, let's say, operations acting on those qubits, like individual gates where you flip a qubit from up to down. And then it is up to you to define the task still by forming the reward. So one important question is here, do we have a model of this world, of this environment on which we are acting? Obviously, that would be very useful because then we can predict what will be the effect of our actions. So then we can plan ahead. And in physics, oftentimes we do actually have models because we have a Hamiltonian of our quantum device. We have fabricated to realize this Hamiltonian. Nevertheless, even in such cases, it still involves some effort to calibrate your quantum device and find out the true parameters of the Hamiltonian. And there may be other aspects like the noisy transmission line through which the signal travels from room temperature down to your quantum device. So there may be many unknowns. And therefore, it's also good to talk about something that is called model-free reinforcement learning, where you don't assume that you have any model whatsoever of your device or of your environment. And so that's what we are mostly speaking about today. So you have this situation, again, your qubits, your quantum device, all the operations you can perform, but you don't, or the algorithm that will teach this neural network does not assume that you have a model available, even though maybe in the back of your mind you do have a Schrödinger equation, but you don't have a model. And then the question is how to represent the policy, this mapping from observations to actions. And there are many different ways, but one famous way that describes a whole class of algorithms is given in the way shown here, namely by way of a probabilistic policy. So given an observed state, what's the probability to pick different actions? And as you change the policy, you're changing these probabilities of picking different actions. And the good thing about this is probabilities are continuous. So even if actions are discrete, you can apply techniques such as gradient descent on such a setting because probabilities are continuous, so you can take gradients. Okay, I will not really say anything more about the details of how these reinforcement learning techniques work that the computer scientists have invented. But by now they have become a really powerful toolbox and there are libraries that you can import. So it's not even necessary to implement them on your own. Okay. So let me go through the first big set of examples, and that's about discovering quantum error correction. Quantum error correction is a field that is very amenable to this kind of approach. And the reason is that it relies a lot on feedback. Yeah, so you let your quantum computer run, you take a measurement, you say, oh, what does this measurement mean? Maybe there was an error, I should correct this error. So it's a typical feedback cycle. And as you've learned before, reinforcement learning is exactly good for such feedback. So these are the questions you could ask. What is the best quantum error correction code in practice on a real device if I know the qubits are connected in a certain way and there's certain gates that I can apply to these qubits, there's a certain noise acting on these qubits, and maybe you as a human don't want to reinvent quantum error correction every time for these different platforms. And so it's a complex game of strategy optimization. So the very first example that we attacked back from 2018 is still very good as a didactic introduction to the field. So imagine you have really a few qubits. You want to talk about a small quantum modules. And these qubits are subject to noise, and you want to preserve the quantum information that is being stored inside these qubits. So you can formulate it like a game. You can say, let me initialize one of the qubits in an arbitrary superposition state. It's unknown to me, to the agent that is trying to preserve this quantum information. I should be able to preserve it regardless of the initial state. And the tools I have at my disposal are, say, gates, operations that can act between the qubits and also on individual qubits, as well as the measurements that I can perform. So in order to display this, we draw a quantum circuit that as time runs to the right. Every line corresponds to one of the 4 qubits. Psi of 0 is stored in one of those qubits. And now I can start applying my actions. For example, control not between these two qubits. So I flip the second qubit depending on the state of the first qubit. It's a kind of if-then operation. And then I can maybe apply another controlled not and another controlled not, or also different quantum operations. And eventually, maybe just by random choice, I will choose to measure one of the qubits. And if you know your quantum physics a little bit and have followed this carefully, then you know that all these controlled knots will have produced a massive entangled state. And by measuring only one of the qubits, I will suddenly collapse everything. And it was exactly the wrong choice of action, yeah, because now I have destroyed my quantum information completely. So in my effort to preserve it, I have destroyed it. But I'm displaying this because in the beginning of reinforcement learning, the computer is in exactly this situation. It doesn't know what to do. It just applies random actions and it gets told that it did the wrong thing. However, if you implement it in some smart way, then it actually does get better. So here I show the situation at different stages of the training. Initially, things are completely random, basically. So they are not good. Eventually, it becomes better. It learns to avoid these catastrophic measurements. It finds an encoding sequence that by inspecting, we know what it corresponds to, so so-called repetition code, discovers that there are smart measurements, so-called parity detection, where you compare two neighboring qubits, whether they are in the same state or not, that do not destroy the quantum state, but do help for the quantum error correction, and it applies them periodically. So once this works for one example, the good thing is now you can also run it on many different examples, many different connectivities, many different gate sets. And so that's what's shown here. So for example, maybe your qubits are arranged in a linear chain and you cannot directly have an interaction between the first and the fourth qubit. So you have to do something smarter than that. Maybe you can measure only one of the qubits, or you can measure all of them, or you have an even different topology. And for all of those, you can run reinforcement learning, and it will figure out a way to cleverly encode the quantum information and then detect whether any error has happened. And if an error has happened, how to correct the error. And because you can sweep through this whole set of topologies, you can then ask simple questions like, what's the increase in the lifetime of such quantum information when I apply this particular quantum error correction strategy? And you can compare the different topologies. So that's enabled by the fact that now, once you have the algorithm, you can really apply it to discover strategies from many different settings. Okay, so on the one hand, it's good. So it's really from scratch, no knowledge of quantum physics. For the agent, it's really just you can apply actions 1 through 17 at every different time step. In the end, you get a reward, some number that tells you how good you were, and then you try it again, and you try it again. So the agent has no clue of quantum physics and yet comes up with strategies that, at least if you had discovered them in the 90s, then you would be as famous as Peter Scheu. Okay. The advantage of this is also, since we start from scratch, you are not limited to these standard quantum error correction strategies. So we also ran examples where it found really nice quantum mitigation strategies where it set aside few qubits in order to measure aspects of the noise and then use that knowledge in order to correct what happens on another qubit. So this is already quite interesting and was not known before. But it does not scale very well because we are simulating all these 4 or 5 qubits, and the number of possibilities really grows very quickly. So the question is, how can we go to more qubits? So that had been our question since back then in 2018. And now I will tell you about the more recent progress that we have made in this topic. It's becoming urgent now because there's all kinds of experimental demonstrations of quantum error correction on, say, systems of 10, 20 qubits, 50 qubits, depending on the platform. So you want to reach this level of qubit number and to propose for all these different platforms that have different connectivities and different gate sets, what would be good quantum error correction approaches. And so the main message here is that in order to enable the computer to do that, you should help it a little bit. You should put in your knowledge as a physicist, yeah, because there's no point in the computer having to rediscover everything that physicists have learned over the past 30 years or so. So we, for example, in this case, we will use the known structure of quantum error correction approaches. We know that there's an encoding stage, there's the detection stage, there's maybe a decoding stage, and so on. So we will split it into these stages. Also, second, we already know that if I give you the quantum error correction code, the logical states into which you have encoded your original information, then there's a well-defined way to check whether this particular code is immune against a certain set of noise. So these are called the Nilda-Flam conditions. So if you tell me what's the noise acting on your quantum device, I can tell you whether your logical states will be immune against this. And then there's the issue of efficient simulation. So if you just run your your simulation of a quantum device on this exponentially large Hilbert space, then very quickly you will run out of steam. And even for 20 qubits, completely forget it, because in reinforcement learning, you have to run the dynamics many, many times, not only a single time. So the good thing is if you concentrate on this very large class of stabilizer codes, of which the surface code and many other famous codes are examples, then you can get away with only so-called Clifford gates. And Clifford gates, for anyone who has never heard about it, are just 90-degree rotations. So you're allowed to rotate qubits by 90 degrees and do similar things for 2-qubit interactions, but nothing more complicated. And it turns out those can be efficiently classically simulated. So that at least already gets rid of one big bottleneck for us. Okay. And so here's one of the two examples I want to show you that are very recent. So the first example is about encoding, successful encoding. And the setting we want to imagine is we have a noisy quantum channel across which we want to transmit quantum information. So we want to encode our original state psi into some logical entangled state of multiple qubits that we then want to send across this channel. What this means in particular is that we assume that during the encoding, there's not yet any noise. It's only after that encoding that we do have noise acting. And so in order to get things really efficient, we will be using a technique that is related to the Clifford operations that I just mentioned of so-called stabilizer representations. So the idea is very simple and has been around, of course, for a long time in quantum computing. Instead of describing the quantum state by its exponentially many amplitudes and some expansion on basis states, you describe a given quantum state by listing the operators for which it is an eigenvector. And these operators even have a particular form. They are products of Pauli matrices. So X is the sigma X Pauli matrix, I is the identity, Y is the sigma Y Pauli matrix. So if you have a 4-qubit state, for example, you would say, oh, if I apply X, I, Y, Z onto this particular state, it's a +1 eigenstate, so eigenvector to the eigenvalue +1. And if you have 4 qubits, you would list now 4 of such Pauli string operators, stabilizer operators, for which the given state is an eigenstate, and it will be uniquely specified in this way. And the beauty of this approach is you can describe extremely highly entangled states in this way with very few pieces of information. And so once you apply Clifford operations, which are these 90-degree rotations, they would just say turn a Z into an X, or maybe change these entries in 2 places. So they just change your stabilizers, but in very simple ways. And that's why they are so efficiently simulable classically. Okay, so now what my little agent does is during this game, it will build up a quantum circuit by again applying these gates like a Hadamard or controlled knot. And for each of these gates, I know how my stabilizers will evolve in a simple way. Now, I'm interested not in describing a particular quantum state. I'm interested rather in a logical subspace that still includes at least 2 different quantum states, so as to encode the quantum information. So even though I have, I guess, 6 qubits here, I will only list 5 stabilizer operators in order to still have a 2-dimensional subspace. All these stabilizers operators, when applied to the logical subspace, will yield +1 as eigenvalue. And whenever one of the gates is applied, all of them will actually change, but in a very simple way. Okay. And so now what's the setting for reinforcement learning here? I will give you the error operators that describe the typical noise that happens. For example, I can flip a qubit, I can change the phase of a qubit, maybe I even have correlated errors in some setting, depends on the setting. I will give you the qubit connectivity that determines between which qubits I can apply gates. And otherwise, I also will give you the gate set that is available in this particular hardware platform that you're interested in. And then what will happen is that at each time step, the reinforcement learning agent will pick a particular gate. This gate will be applied, so it will be added to the quantum circuit. It will therefore change the set of stabilizers that describe my subspace as it evolves. And then for the agent to be able to take the next step, it needs some observation. In this case, the observation is not an actual measurement, but it's just a representation of this logical subspace. So in other words, it's a representation of these stabilizers, which can easily be represented by a kind of binary matrix. So it's not that difficult. And then this loop goes on and on and on. And the goal, of course, of this agent will be to discover a good logical subspace that is immune against the error operators. And so that goes together with constructing the reward function, because I have to describe the task in terms of a reward function. So if you give me the error operators, for each of these errors, I can use the Niller-Flum conditions, which I don't write down here, to check whether the given logical state that I currently have according to my quantum circuit would be immune against that particular error. If yes, then I set a number k equals to 0. If no, I set k equals to 1. And then I construct a reward that is just the negative sum of all these k's. So in the ideal case, if I'm immune against all of these errors, it will just be 0. Otherwise, it will be negative. Negative reward is bad. So it will try to avoid that situation and want to become better and better and eventually become immune against all the errors. Yeah, so that's the thing that we construct for the reward. That's the first ingredient here to go to many more qubits by using the Niller-Flum conditions for constructing the reward. And then the second ingredient is to really become efficient. So this is a more technical part, but it's still important to become really efficient in our stabilizer simulators, because even though they are efficient for classically simulating the evolution of many qubits, you can still make it even more efficient. And so in the literature, the most well-known stabilizer simulator is called STIM. Maybe some of you know it. But we wanted to have the reinforcement learning agent execute many quantum circuits in parallel. That's a technique in machine learning that you run batches in parallel. And so we wrote a particularly fast parallelized stabilizer simulator in this framework called JAX, and it's really much faster than STIM. Okay, and so here are some of the results. So you can vary the number of physical qubits you have available. You can vary the number of logical qubits into which you want to encode the quantum information. And then this, if you run it, it will figure out sooner or later what are the particular encoding circuits and codes that you arrive at. So each of these dots even stands for potentially many different quantum error correction codes. Not only do we discover these codes, but we also discover the associated encoding circuits for the given gate set and for the given connectivity. And we do so simultaneously. And here you see 17 qubits, and we can also go to 20 qubits and so on. Here's another aspect that is really nice. So instead of just trying to find a quantum error correction code for a particular situation, you can also train an agent that would be able to solve a range of different problems. And what we did here was to say, okay, here's the noise strength. For example, the bit flip probability is different from the phase flip probability, and you can vary these strengths. And then we trained an agent to be simultaneously good for all these noise models. So you announce the noise strength to the agent, and it will immediately know internally what it should do in order to encode the quantum information. And this works better than the alternative, which would be to retrain an agent for all these different noise strengths. Okay, so that was the first part, discover good quantum error correction codes and the encoding circuits. So here's another thing that will happen if you apply this on real hardware, because even during the encoding, you might have errors, and these can spoil the whole game. So what could happen is, immediately at the beginning of your calculation, you got an error in one of the qubits. Now, if you then apply one of the single qubit gates, this error gets transformed to an error that looks different. That's not so bad. But if you apply a controlled NOT gate, then this error actually propagates into another qubit, yeah, because the first qubit is faulty, now the second qubit is faulty. And that can be terrible, that can have terrible consequences, because your quantum error correction code is only able to correct up to a certain number of errors. Now this error proliferation will spoil the whole game, because suddenly you have too many errors, you cannot correct them anymore. So what to do about this? Well, that's the domain of fault-tolerant quantum computation, where you really want to be able to rule out this bad proliferation of errors. And so one technique that people introduced conceptually relatively recently is the so-called flag-based technique. So the idea is to introduce extra helper qubits, these flag qubits, and to let them interact with your data qubits in a very smart way, so that at the end you can measure the flag qubit, and if it has been changed, if its state has been changed, then this will announce, be careful, there are too many errors going around here, and you should restart. You should restart your logical state preparation. So the problem with this is it's relatively hard to discover these complicated quantum circuits that will announce in the correct way that you do have too many errors. And so we set about to solve this using reinforcement learning in collaboration with a group of Markus Müller in Aachen, who is really an expert in quantum error correction. And so here just briefly is what we did in the end. We target a particular logical state. So we say for this particular quantum error correction code, we want to target the logical 1 state. Then we let our agent run with all the techniques that I introduced before. And in the end, we will want to have the following. First, we want to minimize the distance to the target state. Oopsie. Minimize the distance to the target state that is given in terms of its stabilizers. And also we want to make sure that all the harmful errors that get flagged. So whenever you would have too many physical errors inside the logical code space, then the flag qubit would say, you have to be careful, please try it again. And so that worked really well. Here we have results. I'm not quite sure why it wants to switch off. Here we have results for different connectivities. These are connectivities coming from the Google computer platform, and they work very well. We then can compare them against what exists, and we find indeed that in some cases the strategies that existed in the literature were not as good as the strategies that have now been discovered by reinforcement learning. For example, this number says the number of 2-qubit gates, and you can reduce them from 20 to 12. The second number indicates the number of ancilla qubits, these flag qubits, and you can reduce them from 6 to 2. So these are quite massive improvements and really important for the current stage of quantum computing, where you're fighting for every 2-qubit gate and every qubit that can be gotten rid of. Another interesting observation is that transfer learning helps. So you can train these agents, say, on a full connectivity, and then continue training after having switched to a different connectivity. And this actually works better than if you were to start from scratch on the different connectivity. So it keeps some of the insights that it had discovered earlier and really is able to transfer them. And so here's one very recent result. So we applied this up to the Surface 17 code that works on 17 physical qubits. And there, for the first time really in this setting, we're able to discover such a flag-based fault-tolerant preparation circuit. Okay, so this works really well. Now, so far, everything I told you is reinforcement learning being trained in simulations. Yeah? And so that's also one reason why we have to make sure these simulations are really fast. But what about then training and deploying in actual experiments? And so for that, there are actually two big challenges that come up. The first is we need to extract the reward from the actual experiment. And that means we do not have any ways of cheating, of looking into what is the actual quantum state currently. No one is going to list for me all the stabilizer operators. I have access to nothing else but some measurements. So really, this is one challenge to extract the reward from the experiment. And the second challenge is, if you think about feedback, and you think about hardware platforms that are relatively fast, like superconducting qubits, where individual gates can be on the order of 10, 100 nanoseconds, and even measurements is only a few hundred nanoseconds, then that means your agent implemented as a neural network has to be able to respond within that time scale. So suddenly less than a microsecond. And that is really challenging for a neural network to do. And so we teamed up with a group of Andreas Wallraff in Zurich and especially Christopher Eichler, who by now has moved to Erlangen. And so they are world experts on superconducting qubit systems, and we tried to implement experimental reinforcement learning on such a system. So prior to that work, there had been a little bit of work on reinforcement learning on experimental platforms. For example, the Birchuk group worked on designing good quantum gate sequences. The Natalia Ares group in Oxford was looking into how to tune up their quantum dot systems. But none of these required real-time feedback, so feedback that has to happen within the coherence time of the qubit and has to be really fast. And so what we implemented together with them was really, for the first time, some real-time feedback control on a quantum experiment via reinforcement learning. And so there would be a single transmon qubit being measured, then the measurement is being fed into a neural network implemented on a field programmable gate array, and then it would decide on an action and send down a pulse back to the qubit in order to change the state of the qubit and so on and so on. And we managed to do this in less than a microsecond cycle. So first there was a lot of technology optimization involved, like fighting for every nanosecond of multiplication and addition on the FPGA, obviously. But also at least some interesting new idea. So usually if you have a neural network, what you do is you feed the input into the first layer, and then layer by layer, you calculate both linear and nonlinear operations in order to finally arrive at the output layer, and then you announce the output. Now this unfortunately would take too long in our case. So what we did instead was, while the measurement data was still arriving, we would feed the first few nanoseconds of the measurement signal into the input layer. And then the network starts already its computations, and we are still feeding new measurement data into the system. So every new hidden layer would receive an extra chunk of measurement data until finally the last pieces of measurement data arrive at the output layer. So that meant that the total latency added by the neural network was only an additional 50 nanoseconds, addition to these several hundred nanoseconds that the measurement takes. And so that really enabled the whole thing. And now you can really let it run on the experiment. What happens is you take 1,000 trial trajectories, then you upload these trajectories together with the rewards onto a PC. On the PC, you apply one of these standard reinforcement learning algorithms, you update the network, and then you download the updated network parameters onto the FPGA. You again run 1,000 trajectories and so on. And so that works really nicely. So after 3 minutes, you have trained the system, and then you can start analyze the strategy that the system has found. So here the task was still very simple. We are only dealing with a single qubit, or here we treat it like a qubit, so with an additional level. The task we gave it was to reset to the ground state, and then we can plot the actions that it suggests as a function, say, of the input, which is the noisy measurement signal. And so we represented the noisy measurement signal in a two-dimensional plane by some signal processing. And then, for example, here you find, oh, in this region, the agent suggests that you should apply a pulse that would take you from the first excited state down to the ground state. And in other regions, it will suggest different actions. So that's quite interesting then to see what is being suggested. Okay. And so then just to wrap up this reinforcement learning part, there are many other questions. So for example, can we do anything on the scale of order of 100 qubits? And the answer is yes, we can do that if we are smart about defining the challenge. So here, this has been done for quantum circuit optimization. Can we employ the model? Yeah. So far, this was all model-free. We are pretending that we don't have a model of the quantum device, and we are only learning about it indirectly. But sometimes our model is good enough, and then we might choose to use it. And we introduced something that we called feedback grape. For all of you doing control theory, you may know about the grape gradient descent pulse engineering technique. And we managed to include feedback and applied this actually to discover better quantum error correction strategies for one of the bosonic codes, which are nowadays actually the most successful quantum error correction platforms. Okay, so in summary for this part, reinforcement learning is really a powerful tool for discovering strategies in quantum devices, even up to real experiments. But of course, there are still many challenges. How do you make them fast enough? If the strategy becomes more complex in the real experiment, then your neural network also needs to grow and so on. So the question is how much time I still have. Still 10 minutes or something? Okay, that's great. So in the second shorter part, I want to tell you about a very recent work that is not yet even out on the archive, but you're going to hear about it. And that is, we can entitle it Artificial Scientific Discovery of Scattering Setups, and you will see in a moment what I mean. So in quantum technologies, we often have setups like this. So now we're even leaving the realm of qubits. We're just talking about something like an optical cavity, maybe coupled to some mechanical elements. We're transmitting a light beam and trying to do something interesting, like converting from microwaves to optical radiation or something like this. And this exists not only in one variant, but in many, many different variations with many different functionalities. And people play around in order to discover interesting new setups. So the question is, how can we automate this process instead of just an expert coming up with a new setup? And that falls into this general scheme of artificial scientific discovery, where you would maybe come up with smart experiments, then actually do the experiments, analyze the data, generate new hypotheses, and expand the space of hypothesis, come up with new experiments. And so the cycle goes on and on and on. And here we are focusing on a particular part of it, namely coming up with interesting new experiments. And so this goal has a long-standing history of artificial scientific discovery. So for example, even back in the 60s and 70s, people were writing first computer programs that would look at complicated mass spectra and figure out what molecule stands behind all these fragments that have been discovered. More recently, there's this so-called robot scientist, Adam, and its successors that have been used to do functional genomics, so figure out which genes do which things in yeast, for example. And then there has been a great series of papers by Mario Kren, who's currently a junior group leader at our institute, but started out as an experimentalist in the lab of Anton Zeilinger for discovering quantum optics setups, for example, maximizing multi-photon entanglement. And there are, of course, many more ingredients for artificial scientific discovery that I list briefly here. For example, you can try to do active learning. What is the most economical measurement to perform to learn the most about a given experiment and so on. Now, there have been a few lessons in this field, and these lessons are, for example, the choice of the representation is really critical. How do you even represent the search space? Then the definition of the goal is equally critical. A full enumeration of solutions is sometimes good if you can do it, but you need techniques to restrict this exponentially large search space of possibilities, or maybe introduce a heuristics. You should also make use of human knowledge, and above all, you aim for interpretability. So this is maybe what sets it apart from standard machine learning, where maybe you're happy if you just get a neural network that performs well. But here the idea is set up your representation and your search such that you can interpret the results and generate new insights. And so what you really want to do in the end is concentrate on asking questions and interpreting the answers as opposed to searching through the space of solutions. So back to our scenario. First, choose a good representation. Now, in our case, we realize that these experiments, as different as all of them look, oftentimes can be represented by a simple coupled mode theory or tight binding model, depending on which community you come from. Yeah. So here you have an optical mode, here you have a mechanical mode, they are coupled to each other, and the Hamiltonian can look relatively simple. So that seems a natural representation. This coupled mode theory is a sweet spot between too microscopic, where you go for optimizing all the details, and a very high level description. And then you want to describe the class of possible goals. So in this case, we aimed for scattering experiments. Yeah. So scattering just means you send in some waves, optical waves or microwaves. You get out these waves in a new configuration after interacting with the device. You describe that by a scattering matrix. And so what you can aim for is to find the device or this coupled mode graph that would realize some desired scattering behavior. And so then you can start playing Lego, so to speak. You can say there are different building blocks. These are the modes that I have. Maybe I need some additional modes, not only those that couple to the outside world and with respect to which I describe my scattering. Then you will want to couple these modes, but you can also do this in different ways. You can couple them in a simple way, but you can also couple them in a way by parametric interactions that can generate two photons at the same time and generate squeezed states and so on. And all of these different ingredients may also carry different costs. For example, some couplings are very easy. You just bring the two modes together. Some are harder to realize. And then you have continuous parameters that you want to optimize as well. Yeah. So for example, the coupling strengths you want to optimize. So you want to optimize continuous parameters. And one smart way to go about this is to introduce dimensionless combinations of these continuous parameters. Okay. And so now I come to the core of this. What you want to do is carry out two different optimizations at the same time. So given some target scattering behavior, you can try to set up a little coupled mode circuit, and it comes with different parameters. These are the coupling strengths, for example. And you can try to optimize by minimizing the deviation between this scattering matrix realized by this coupled mode circuit and the target scattering matrix. And so if you can take this difference between the scattering matrix down to 0, then you can say my graph is valid, else it is invalid. And now there's an interesting observation, namely, if you can get a valid graph to work, then of course any graph that is even bigger and has more couplings available would also work in a continuous optimization because it has more freedom. On the other hand, if a graph already doesn't work and then you even take away some freedom, that also will not work. So you can eventually build a library of valid graphs that will work and invalid graphs that don't work. And by that process, you can drastically speed up your search through the space because very quickly you can rule out many different solutions that certainly will not work. Okay. And so I will skip this, but I will go directly to a few examples and then I wrap up. So for example, you could say, I want something that people call a directional coupler. So you have two waves coming in, and then the output should be summed up in a single wave that goes to the right in this case. And once you run the algorithm, you find a few irreducible setups that cannot be simplified any further. Each of them cannot be simplified any further without breaking the functionality, yet all of them look different. And they have different, say, numbers of couplings or different numbers of parametric couplings. So depending on your experimental capabilities, you may opt to go for one or the other. So that's a nice feature of all of this approach. And here's just a quick way to visualize how much we reduce the search space by this smart scheme of ruling out many solutions. And so here's a remark about how interpretability gives rise to generalization, which is, as you remember, one of the big goals in this artificial scientific discovery. So once you look at this and you look at it a little bit more closely, you realize there are certain building blocks in it. And then you can try it out and find quickly, oh, we can generalize this thing for more inputs. And you can even look at how the dimensionless coupling parameters should be generalized for this larger number of inputs. So clearly, at least one goal of artificial scientific discovery has been achieved in this particular setting. You can also solve for a class of setups. So maybe your target scattering matrix contains still some parameter. And then what we do, we solve actually for one particular value of parameter. We then fix the graph and redo the continuous optimization for other values of the parameter. And eventually we do some symbolic regression to find out not just numerical values for these couplings, but actual formulas for these couplings. And so here's just one example, a so-called fully directional amplifier. So you want to amplify fragile quantum signals to much larger amplitudes going through your magic amplification device. And there were some setups suggested in a work by the Michel Devoré group, actually relatively recently. And when we applied our technique, we actually find simpler solutions, even though they were pretty confident that they did have found the simplest solution. So that's an example of the automatic search does not make any mistakes according to implicit assumptions or so. It just goes through all the possibilities. And we then also find the actual values of these of the entries of the scattering matrix with respect to the parameters. Okay, and there are many, many more examples. I will not comment on them further and just put up this last slide where I show you some of the references that I covered. And thank you for your attention. And now I can take questions.
Okay, thank you very much for this extremely interesting talk, and especially for the effort essentially to make it really didactic and really interesting. So go ahead and ask questions. Wait for the mic, okay? So.
My question is about the first part of the talk, the part where you talked about the the flagging qubits and all those techniques for detecting errors. So you say you trained your reinforcement learning on 3 goals, but most reinforcement learning algorithms like SARSA, Q-learning and its variants are designed for a scalar reward. So how do you take into account what do you want to prioritize, or do you let it run free, or what?
Okay, yeah, that's obviously a very good question. So yeah, if you want to optimize something, in the end, you can only optimize for a single scalar quantity. So what happens here is the distance to the target state is something that we know eventually can become 0.
Yeah.
And then within the space of where it has become 0, we can ask for more. We want, for example, that all the harmful errors get flagged. So that's another piece of the reward. And then there's another condition here. So what we do is really we set up a reward function that has different pieces that are weighted by different weighting factors that are chosen in a way such that we know that at first it will really take the number 1 priority down to 0. And then it will also try to become as good as possible in the other priorities. There's a little bit of choice of the different weighting parameters. So for the different tasks we went through, we also had to carefully adjust these weighting parameters. But you would see it at the solutions, yeah? If you choose the wrong weighting parameters and then all the time the distance to the target state is bad, even though all the harmful errors get flagged, then you know that this is not yet the right solution, yeah?
So please.
Thanks for the very nice talk. I had a question about the last part in the scattering matrix.
Yeah.
Was that just for the linear scattering, or you also optimize kind of quantum states and nonlinear scattering?
So here we completely remain in the realm of linear scattering, which can include amplification and so on, but still is quadratic Hamiltonians. We do track beyond the scattering matrix also the quantum noise. So that's why we are able to say whether we do have a, say, quantum noise limited amplifier and so on. So that's already pretty good. But yes, it's completely linear scattering. But as you probably also know, there's a huge range of applications like circulators and so on, isolators, and a huge community who go through one linear scattering setup after the other. Now, of course, it's equally interesting then to target also nonlinear scattering. And we certainly have this on our list. There, the challenge is a little bit that immediately it becomes a little bit more platform specific, yeah, because different modes get coupled. Now, how are their frequencies in relation to each other? Whereas the beauty for these linear coupled mode setups is once you have discovered such a graph, you can implement it in very different hardware platforms that it will probably work. Yeah? But that's not something that it's not the fault of artificial scientific discovery. It's just intrinsic property of linear versus nonlinear devices. Yeah.
Some more questions? I'm curious, just in particular, essentially the youngest people here, because our students are at the level of PhD, okay? Go ahead. Florian is very approachable, okay?
Well, I'm not so young, but Yeah, thank you for the talk. It was really nice. How about doing, adding an additional layer of complication or sophistication, adding kind of a multi-agent reinforcement approach to
Okay, so what would be the tasks of the multiple agents? Usually they would either have to collaborate or fight against each other, right?
Yeah, that's the point.
For example, if you think of quantum error correction, so nature or the noise is bad, but it's not malicious. Otherwise, I would say, yeah, maybe we take an agent that is able to change the noise that is acting on the system, and it has to fight against the other agent that is trying to come up with a good quantum error correction strategy. Maybe in some scenarios, this might even be good. So you are convinced you have a relatively good strategy, but you want it to be actually completely generalizable, not only work for these particular error operators, but much more general. And then it could be a smart idea to make the goal of another agent to figure out the small details or the error operators that are really bad for this one. So maybe it could help to test the robustness, so to speak, in a kind of adversarial way. But I really didn't think about it before your question. So,
and another question that, when you were telling us about the real-time reinforcement learning, that reminded me about this kind of self-driving labs, right? In which you have some kind of robotic part that is driven by a Bayesian software or whatever, and then there is no human in the loop intervention. So somehow this idea, right, going in the direction that the algorithm will be learning by real time and basically taking its own decisions, right?
Yes, that's right. So the one thing about the automated labs is that, or the one thing about reinforcement learning in the real world is typically that it's very costly to do every single step. And so people try to avoid that. Also, you might even break the equipment, right? So people try to do as much as possible in simulations, and then maybe learning a model from observing the usual dynamics. And so real world reinforcement learning in such settings requires you to think very hard of how to minimize the number of actions or trajectories or samples that you take. And what I showed here, the robot scientist Adam and so on, there is no reinforcement learning in there. There's just some smart programs that work more in the Bayesian sense. Okay, I have some knowledge already. I take in the next example. What does it mean? And now what should I ask next? This kind of things. Yeah.
Thank you very much.
Yeah.
Oh, yeah.
I really enjoyed your talk. I have a quick question about the second part where you presented how you generated these graphs for the scattering matrices. And did I understand correctly that different graphs can result in the same scattering behavior, right?
That could happen, yes, okay. I guess, yes.
So I was just wondering, like these graphs, how do you generate them, like in a deterministic way or in a probabilistic way?
No, it's all deterministic, and we are pretty proud of that because it also means that we don't lose any solutions. So what happens is really we go, so to speak, we go first for fully connected graphs that are the most powerful, so to speak, but also most expensive experimentally, of course. And we just start with, so we start with a few modes and then it doesn't work. Increase the number of modes, still it doesn't work. At some point it starts to work. And then from that point on, we can reduce the complexity again. And this is what is shown here. So this would be a fully connected graph with I don't know how many modes. And then you try to reduce the complexity. And eventually you come to situations where you cannot reduce the complexity anymore without breaking the functionality. And these are the irreducible graphs that we end up with. Yeah. So we really get a full, complete overview. We cannot possibly miss a solution. Of course, that also means we can never do this for, say, graphs with 100 modes or so. Then it would just be too slow.
So just like to follow up on that, like the point where you start is then like a single node and you grow from
there. I could start with a single node or the number of modes that correspond to the number of scattering ports that I'm interested in. And then I will probably find that this is not yet sufficient. So then I have to increase, and eventually I can decrease the complexity again.
Okay, really interesting. Thank you.
Yeah.
Hi, thanks for the talk.
Yeah.
I was curious whether some of these techniques have been used for the discovery of bosonic codes. Like, what's the state of the art on this?
So I don't know about code discovery, not something that I'm aware of. What we did was to discover a better strategy. So the kind of feedback, so you already know your code, for example, GKP code, but now you have to do feedback, measurements, and stabilization of the logical subspace. And for that, we used this model-based, in that case, technique in order to find a better feedback strategy that then discovered some non-Markovian feedback that is not so easy to discover by hand, so to speak, but for a neural network, it works. And then it increases the lifetime by a factor of 2. So you may know that the GKP code is currently the most successful error correction code, and it had increased by a factor of 2 the lifetime of a logical qubit as in comparison to the best components, cavity and qubit and so on. And we increased it by a further factor of 2 using this technique. Yeah. Mm-hmm.
There was another question here. We're coming to the end, so somebody else has a question in mind. Go ahead.
Thank you for your talk. So if I understood correctly, in the first part of the talk, you are using a reinforcement learning agent to do kind of a smart sampling of the quantum gate that you have to apply the teacher step, right?
Yes,
So
yeah.
I was wondering, has anyone tried to use other efficient sampling strategies like Bayesian sampling or stuff like that, or how do they compare? Why a neural network instead of any other model?
Well, okay, what would be the alternatives? You could do some brute force search. That wouldn't work because the number of possibilities is just too large for these strategies. You could maybe try some genetic algorithms, and I'm not quite sure whether maybe some people have tried that, but certainly it was not on the level of the performance that we are seeing here. So the good thing about reinforcement learning is simply once it has seen a solution that works a little bit better than the baseline, then it will latch onto that and will reuse that knowledge in order to more quickly proceed towards a good solution. So basically, it's a sampler that adapts itself and becomes, every time it retries the whole thing, it becomes a little bit better.
Maybe the last question. Anybody? Yeah.
Thank you for your talk. If I understood correctly, when you use classical neural networks, you're feeding in the data you feed in has like the operations have a very short time, like nanoseconds.
Like in the experiment, yeah,
yes,
yeah,
in the
yeah.
experiment,
Okay,
have,
yes,
like,
exactly.
nanoseconds,
Yes.
and there are problems with using classical neural networks because it's very short amount of time. My question is this the motivation for using quantum neural networks because it has much less time?
Okay, well, the question is whether they really need much less time is actually not so true, because they would also rely on the same quantum operations that are running in the quantum computer themselves anyway. So the time scale would automatically be comparable, and it wouldn't probably be able to do any steps in between. But still, it's a motivation to search for better hardware approaches for machine learning. So you could imagine replacing the FPGA by, say, some, in this case, classical electronic circuit, maybe even implemented on the same superconducting platform, maybe using some Josephson junctions or something, that de facto replaces an artificial neural network and is more working in an analog fashion. So there's this whole field of neuromorphic computing. it hasn't yet been implemented. Yeah, so there's the research on neuromorphic computing, and then there's the this kind of research. But at least in certain proposals, we have already proposed that one should look into this. But the actual experimental implementation is challenging. Yeah, because I mean, people looking into neuromorphic computing also look, say, into optical setups, including us. But that wouldn't. So here you have your little superconducting qubit platform, and here you have your optical neuromorphic device that there's a certain mismatch in between. So you have to think very closely about how to implement it in hardware, actually.
Okay. So thank you very much, and please join me to thank Florian for this excellent talk.